This is basically a PhD work of one of my PhD student, Rakesh Raut, who is there in the audience. Most of this work that I'm going to present is part of his thesis. I will just serve as a spokesperson here. So if you see our planet, there is a very interesting situation, that is, if you see our neighboring planets, the Venus or the Mars, you see that the CO2 concentrations are abundant in both of them. They are about 95%, whereas in our planet, the CO2 content is very less. It is in the trace amount, it is around 400 ppmv compared to the 95% in the other places. Now, we need to understand why this CO2 cycle is very different, because that is very crucial in understanding why we are finding water in a liquid phase, because the temperature is such a stable at around in a zone where water can survive in a liquid phase. So if you try to understand the CO2 cycle, most of the CO2 supply to our planet are shown here. If you see the short term, they sort of influence the high frequency variations, and particularly in few years time scale. But if you see the large time scale of the planetary time scales, what we see is the major CO2 suppliers like the volcano, or the removals like organic carbon burial, silicate weathering, or the supplies like organic carbon oxidation and carbon release by sulfide oxidation, they all act in tandem to control the CO2 that you find in our planet. Now, if you look into some number, the amount of carbon that is present in our planet, the sedimentary carbon is about 610,000 in 10 to the 17 grams, compared to atmosphere, which is only 880 into 10 to the 15 grams. So there is a quite imbalance in the carbon reservoir, and the atmosphere only constitute 1 by 70,000 of the carbon that we have, and most of the carbon is actually locked in the carbonates. And that plays a significant role in controlling the temperature of our planet. How? Because you know that the major CO2 supply, if you try to understand in a conventional way, the amount of CO2 that is coming to our atmosphere, they mainly come from volcanoes. So you put on CO2, and if you see the fluxes, probably in 400,000 years, we should have around 95% of CO2. But there is luckily one removal pathway, which is silicate weathering. So the CO2 produces carbonic acid, and they weather these rocks, which consumes the CO2, and that happens through multiple chemical reactions. If you try to see the silicate or carbonate cycle, the silicate minerals generally are consuming CO2 when they transform from silicate to carbonate in the ocean basin. I'll start with the calcium carbonate that you find in the terrestrial. So if you have a carbonate rock, and if the water and CO2 interact, they provide the proton through carbonic acid, and they release calcium and bicarbonate. These calcium and bicarbonate from the land reaches to the ocean and precipitate out as a calcium carbonate, and they release that CO2. So they are perfectly in balance when it comes to carbonate weathering. Whereas in silicate weathering, there are 2 moles of CO2 consumed to transform silicate rocks into oceanic carbonate, and that's why you consume CO2. And because of this silicate weathering, there has been large changes in the CO2 concentration of our planet. And one of the most significant observations in terms of silicate weathering and CO2 cycle comes from Himalaya, where in 1992 there was a famous paper by Remo and Trudeman. What they saw is there is a significant increase in 87 by 86 is a proxy for continental weathering, and this change in seawater strontium isotope is some level reflecting the temperature decline in our planet. So we were entering into a Cenozoic cooling phase, and during that time there was an increase in silicate weathering, and that is reflected in 87 by 86. So Remo and Rudiman proposed this hypothesis because these changes are synchronous to Himalaya formation, which might have caused tectonism, and their subsequent weathering, because of high relief and stream power, they could trigger intense silicate weathering, And because you have a silicate weathering, as we saw that silicate weathering is a sink of CO2, it can lead to global cooling, and hence we are seeing a climate change. So there is a tectonic weathering and climate linkage that is happening in this case, which was beautifully presented in terms of delta H, which is a proxy for climate, and 87 by 86, which is a proxy for chemical weathering. In India, this was thoroughly studied, and large people have contributed to this story of Himalaya weathering and Cenozoic cooling. And Professor Krishnaswamy from PRL and his group was actively working for this field, and their research actually showed that indeed the CO2 consumption rate for the Himalayan rivers, if you see the bluish color, they are about 4 into 10 to the 5 moles per kilometer square compared to global average, which is about 1. So there is a 3 to 4 times higher silicate weathering that is happening today in the Himalaya. And also they showed that the 87 by 86 ratio, which is used in the previous plot for seawater, is actually much higher for the Ganga Brahmaputra river system compared to world rivers. So possibly the growth of 87 by 86 was linked to Himalayan rivers. They went on to do more mathematical calculation in terms of looking at various numbers and a lot of mass balance equations, but they found in 92 itself that these rivers can account only 30% of the 87 by 86 increase. Yes, there is an increase and Himalaya may contribute, but it can be only 1/3 of it. It cannot be accounted the full growth that we are seeing. This led to a confusion, or the need to study it more to understand what other factors which may contribute to some of the changes or the global Cenozoic cooling, or what we are finding in terms of the growth of isotopic things. How does that occur? In a recent paper, Torres et al. Actually tried to understand this paradox. So they sort of compiled the 87 by 86 is one of the proxy that we have discussed now. And there is another proxy on osmium isotopes, which is a chalcophile element with low residence time in seawater, in contrast to strontium, which is a lithophile element and has a high residence time. They found that there is a mismatchment in the increase, though they broadly show an increase in the trend, which reflects that the continental weathering is much higher during this period, but they are not able to attribute everything to the silicate weathering, as was studied by Krishnaswamy and his group. And these people have come up with the suggestion that some of the osmium isotopic proxies or the evolutions are actually because you have a pyrite oxidation occurring in these basins, which has not been accounted yet. And that's how more recently it has been updated, the kind of carbon cycle that we are seeing, that yes, there is a volcanic degassing that supplies huge amount of CO2, and yes, there is a silicate weathering which is giving you declining the same amount of silicate weathering, but there are various other carbon sinks like organic carbon burial, and these must be supported by some CO2 supply, and these CO2 supplies are found to be sulfide oxidation or petrogenic organic carbon oxidation. The organic carbon oxidation varies from 40 to 100 megaton of carbon per year, but the sulfide oxidation, we really don't know. This question mark itself in the recent review itself shows that our understanding on the sulfide oxidation is not very clear, and the rate and the process through which it contributes to the carbon cycle. How does this sulfide oxidation plays a role in the carbon cycle? So if you have a possibility, if you find these reduced minerals in the continent, and if they oxidize either by interacting with the oxygen, atmospheric oxygen, or by interacting with the water, the aqueous water, then what will happen is they can lead to form a sulfuric acid which is much stronger than the carbonic acid. And once the calcium carbonate present in the land, if they interact with the sulfuric acid, they will liberate CO2, and this CO2 supply has to be quantified and must be included in models to understand what really controls the ocean chemistry. Now, whether it is significant, it is not only significant in the past time. If you see the modern time also, you see lot of acid mine drainage. These are indicators of some of these pyrites being oxidizing and providing a lot of sulfuric acid, and their subsequent dissolution is leading to some of these acid mine drainage. But if you go back in the long time scales also, whenever you see there is a significant change in the trace metal concentration in the seawater, they are largely linked to the oxidative weathering of pyrites or reduced minerals, which we are also trying to see the sulfate concentration in the seawater, which all these evolutions are actually linked to pyrite oxidation. It may be a trace mineral, but has a larger role to play in terms of seawater chemistry and climate. And that's why we wanted to study more about these processes in Indian river basins. Now, there has been recent interest to study about this pyrite oxidation, the rates, and want to compare the silicate, the potential of silicate weathering in consuming CO2, and the countervalence of pyrite minerals and sulfide carbonate weathering associated with that, the CO2 released through these processes. How much CO2 is released during pyrite oxidation and how much CO2 is consumed during silicate weathering, that will decide the net effect of chemical weathering from river basins on carbon cycle. So if you see some of these compilations for three major river systems, you will see that some of them are actually comparable in terms of silicate weathering and pyrite oxidation. In other systems, they are actually much higher than how much CO2 is consumed by silicate weathering. That means these river basins act as a source of CO2 to the atmosphere, and hence this hypothesis of increased weathering will always lead to a CO2 consumption probably is not correct. Does that happen all across the river? No, there are certain pockets where this intensity are much higher. And if you see the rates again on a basin-wide scale, these basins, the cooler climate in the glaciated region, the glacial oxidation helps in releasing a lot of pressure minerals which produces sulfuric acid, and their subsequent dissolutions involving carbonates act as a net source in the mountainous region. Then in the floodplains where silicate weathering actually dominates. So if you try to understand this particular cartoon, the glaciated terrains, the mountainous terrain, are supposed to act as a source of CO2, net source of CO2, because the pyrite oxidation dominates, whereas in the floodplains it is the silicate weathering that dominates over the pyrite oxidation rate, and hence these floodplains act more like a sink of CO2. So there is a difference in these two locations where these weathering pathways are occurring. The total carbon process and the chemical weathering, the land process effect is largely complicated. There are multiple pathways, but if you try to focus on the rate of pyrite oxidation in river basins, they are more or less linked to physical erosion. So if you have more physical erosion, you are expected to release more fresher minerals like the pyrites, which are has a faster dissolution kinetics, may dissolve quicker. So in a basin where the physical erosion is much higher, they may have more sulfide oxidation rate and hence may supply a lot of CO2, unlike some of the transport limited transport limited basins where they serve as a net sink for CO2. This is one of the examples that we quantified for one of the Indian river, where we have showed the transport limited basin. If you are studying at a lower reaches, they act as a sink because the physical erosion is low in this region. So the quantification of the sulfide oxidation is a challenging task. Now, the main reason is the only effect or only memory of this pyrite oxidation is retained in the riverine sulfate data. So once you find the sulfate in a river, dissolved sulfate, so this sulfate can come from multiple sources. It can come from atmospheric deposition, it can come from anthropogenic sources, it can come from hot springs, In addition, they can come from sulfide oxidation, pyrite oxidation, or many of the other sulfide mineral may oxidize to provide the sulfate to the river, or gypsum can also supply sulfate to that. Our interest is to quantify how much is coming from the sulfide oxidation, and luckily the sulfur isotope for pyrites and gypsum are very different. If you see the typical pyrite delta 34S values for pyrites, it is quite depleted, it's a -12 per mil, whereas in case of gypsum they are much higher, it is a typically +17 or +15 per mil kind of number. These are typical numbers, but if you see the real trends, they vary quite a bit, and that's why only sulfur isotope may not be sufficient. You may have to look for some other chemical proxies or isotopic proxies, and one of those successful isotopic proxies are actually oxygen isotope of the sulfate. So because sulfate will have both sulfur and oxygen, you can measure the delta 34S. At the same time, if you could measure the oxygen isotope of that sulfate, probably you can quantify it in a better way. So keeping this in mind, we wanted to quantify the pyrite oxidation for all Indian river basins. So there is a strong interest in my group to understand the pyrite oxidation by using sulfur isotope in Indian rivers. Some of those data I am showing it here. If you see the broad trend, probably you can appreciate is on the upper reaches, like in the Himalayas, they are quite depleted. This size of this symbol reflects the delta 34S, so they are depleted and smaller in size when you go to the upper reaches or the Himalayan, whereas if you come to the peninsular India part of it, they are quite high. So this clearly shows that the Himalaya, the pyrite oxidation is probably much higher, because we know delta 34S of pyrite is depleted. So finding a lower value in this river is actually telling me qualitatively that this is high pyrite oxidation is happening, and we wanted to quantify these things. So today I will focus only on the Indus river system, and I probably some other time I'll discuss more about the peninsular Indian part of it. But today our focus will be mostly on the Himalayan rivers. In Himalaya, we will focus on the northwest Himalayan part of it. And to do that, what we have done is we have collected all the rivers that flow, all the Indian Indus headwaters, and major tributaries, hot springs, groundwater, seaways, every possible water supply or through which we can receive sulfate in the river basin has been collected during July-August 2021, particularly in the monsoon season. We have collected all these samples for multiple rivers. The main reason why we opted for Pyrite Indus is because there are a lot of Tethyan sedimentary sequences where you do find lot of organic shells and pyritiferous limestones. They are supposed to deliver a lot of pyrite oxidation, and also the Indus basin is quite glaciated, and because glacial oxidation, previous studies have documented that glacial oxidation could be important in terms of releasing a lot of sulfate through pyrite oxidation, and hence can contribute to a significant amount of CO2 to the atmosphere. That's why we wanted to quantify. Or the second aspect is because we are evaluating this connection between Himalaya weathering and Cenozoic cooling. Indus being flowing through the northwest Himalaya, we wanted to see if this river basin has a net effect of CO2 sink. That's also we wanted to quantify. The third reason why Indus is preferred is there is a significant analysis of delta 34 is in the lower reaches of Indus, which was done by Karim and Beiser, and we wanted to use the Indus headwater data which was missing. So we wanted to create this data set for the headwaters and include the Karim and Beiser data from the floodplains of Indus, and built a basin-wide scale understanding about the pyrite oxidation in this particular basin. So if you see the water chemistry data, mostly they are if you see the calcium by sodium or magnesium by sodium ratios for the Indus River basin, they're mostly can be explained by silicate to carbonate dissolution. So most of the data, whether they are from the Indus tributaries or the Indus mainstream, even the lower reaches, they can be accounted by silicate and carbonate. Now the silicate or carbonate weathering can receive proton both by carbonic acid or sulfuric acid, and we need to understand whether these weatherings, the silicate weathering and carbonate weathering, is happening through carbonic acid or sulfuric acid. For that, we plotted them in a Piper diagram where the typical compositions of different weathering pathways are shown in the star symbols, and this is the carbonate weathering dominated by weathering happening through sulfuric acid, whereas the carbonate weathering through carbonate weathering through carbonic acid should have no sulfate, so they should be falling somewhere closer to this point. So when we plotted all our data, what we saw is actually most of the data fall closer to carbonate weathering by sulfuric acid and can be explained as a mixture of carbonic acid and sulfuric acid. So it's not completely 100% carbonic acid, but there are three components which could be important. One is carbonate weathering by carbonic acid, carbonate weathering by sulfuric acid, and carbonate weathering by carbonic acid. So we need to now quantify or do a source apportion modeling to find how much is coming from the sulfuric acid, because that is of prime interest for today's talk. So this is the measurement of sulfur isotope in comparison with all the Indian river basins and some of the major river systems from the Tibet side also. So if you see, this is the global, this dotted line, what you can see is the global average number of about 4.5 to 5 per mil of global average river water data. But one thing that is observed is, though there is quite a bit of spread in the delta 34S of Indus headwaters, they are systematically depleted from the global average. That means the pyrite oxidation, because the lower values reflects the pyrite oxidation, these systematically lower value or depleted values of delta 34S for Indus headwater indicates that in this region the pyrite oxidation rates are quite intense. If you see the top plot where delta 34S and chloride by sulfate is shown, you will see a distinct trend, and the distinct trend is the reddish color, which is of a higher elevation among those delta 34S that we saw in the previous plot. The rivers that are flowing through the upper reaches with a higher elevation has a depleted delta 34S compared to that flows through the lower reaches. The lower reaches is around typical of 5 or less than that, so they are closer to the global river data. They are still lower, but they have a relatively enriched value compared to the rivers that are flowing at a much higher elevation, showing that the mountainous river again has a larger role to play in terms of delta 34S. We also compared our data with the floodplain data. So as I have been telling this, the delta 34S is lower for sulfide and higher for gypsum. If you see our Indus headwater data and Indus floodplain regions, so they both of these data actually is depleted than the global rivers, which is 4.8 per mil. And if you see that means the pyrite oxidation in this basin, whether it is a floodplain or a western Indus headwater, both of them are higher. But in the western Himalaya, that is particularly northwestern Himalaya, that is 4.4 per mil depleted compared to the floodplains. That means though the floodplains of Indus still have some pyrite oxidation, the rate of oxidation is much higher in the Indus headwaters, in the upper Indus basin particularly. So to understand this process where mountainous river and its connection, why the pyrite is higher, what we did is we carried out a time series analysis of delta 34S in a upper Indus basin sample. So we collected weekly sample in Leh, that is in the upper part of the Indus mainstream. So when the Indus mainstream enters India closer to that location in a high elevation terrain, we collected weekly sampling and did a sulfur isotope study of that particular location. So there are quite a bit fluctuation in terms of temperature, which goes below sometime closer to 0 during the winter season, and it varies from 0 to 20 degree, whereas the discharge is much larger in the April to June, July, because there is a glacier influx or meltwater influx that comes in. So there is a significant change in the temperature and water discharge, and synchronous to these changes, if you see the discharge trend which starts from May, same is that the delta 34S, which is depleted in the lean flow stages, and it increases at some point of time. But major part where there is a high inflow, that time the delta 34S are slightly lower. So there is a trend that we see. And also the delta 34S and sulfate by calcium, if we compare with various possible weathering, we see that they are actually having a contribution from sulfuric mediated calcite weathering. That value is much closer to the numbers that is observed for Leh. There are not only the pyrite oxidation, there has been some interesting trends in Leh which is not very that has not been observed for Ganga or Brahmaputra river system. If you see the lower plot, so basically the calcium by sodium, which is an indicator of silicate versus carbonate weathering. If you see the Ganga river systems, they are actually, this calcium by sodium values are actually higher when it comes to monsoon period, showing that the monsoon, the carbonate weathering is higher. Whereas in case of Indus, initially they are much lower. The calcium by sodium ratio is lower compared to the other phases, and this is not consistent with Ganga and Brahmaputra. When we compare, to understand that, when we looked into the silica by sodium star, there is also differences we found for Indus compared to Shangpo or Ganga river basin, which are much higher, and they are about 1.6 moles, whereas compared to Indus, where it is 0.25. Probably there is an additional sodium supply which we are not able to understand. Can be some of these mirabilites or sodium supply from hot spring could be one of the reason. But most importantly, this difference in trend where we see a silicate weathering dominancy during summer season, we sort of emphasized or looked into the importance of temperature in regulating the silicate weathering than the runoff. We quantified these things using the delta 34S and delta pyrite to understand how much of the sulfate is coming from rain, hot spring, pyrite and gypsum. I'll not get into these details because we will again discuss that part in the spatial distribution. We did see that the sulfate pyrite or the cation silicate or the F pyrite is sort of declining somewhere between May, June, July, where there is a significant water flux, and this is much higher during low flow stages. If you have a low flow stage, we see that the pyrite oxidation is high, whereas in the high water flow, we see the pyrite oxidation is lower. And one of the hypotheses, this is interesting because when you have a large water flux, it is expected to erode quite rapidly, and hence you are supposed to have more oxidation. But the possibly the linkage why we find lot of pyrite oxidation during low flow stages, one of the main contributor for this oxidation is oxygen, and the diffusion of oxygen into subsurface during the monsoon is limited because you have a high water table. But during low flow stages, when the water table is relatively lower, it can reach to a level where you find unweathered pyrite minerals, because on the surface part of it, because pyrite is a rapidly dissolvable mineral, so they are not found in the surface regime. You may find a silicate found, you may find a carbonate found, but the last part that you find is a pyrite found. And if you have a low water stage, the atmospheric oxygen can diffuse into the subsurface and reach to a level where it can oxidize the pyrites, and hence in the low stages it is expected to have a more pyrite oxidation and supply of cations and sulfate through this process. Now that we know that the diffusion of oxygen plays a role in terms of seasonality of pyrite oxidation, we wanted to come back and understand what happens at a spatial scale. On a spatial scale, we measured two important aspects. One is delta 34S sulfate, which we discussed in some detail. And we also measured, as I mentioned before, that oxygen of sulfate, this SO4, this O and S both are measured. So if you plot them together, this is the global distribution, the histogram that you can see here. So if you plot them, and also the difference of delta 18 sulfate and water, delta 18 water, if you measure the, so here the water is actually the, because you have the groundwater delta 18 is often links with the, often mimics the average annual delta 18 value of rainwater. So we have sort of come up with a amount weighted delta 18 of water, and that has been taken care here. So if you see those values, they are sort of fall closer to the pyrite end member, or most of the data actually fall, particularly if you are looking at the mainstream of Indus, they are sort of falling in a zone where the oxidative weathering of pyrite is expected. So these isotopic signals are more reflective of pyrite dissolution. We can do a mass balance calculation using a Monte Carlo simulation where delta 18 of sulfate will require oxygen. So its delta 18 value is needed. That oxygen, if oxidizes a pyrite, that isotopic fractionation factor must be accounted for. Delta 18 of water, the interactive water that is involved in this dissolution, that is important, or the fractionation factor of delta 18 sulfate and water is needed, because when you have a sulfate and it is going to liquid phase, there may be small but appreciable isotopic variations. If this all goes into a model, we should be able to calculate how much of sulfide is coming through pyrite. So these are, we can do this on an inverse modeling, or we can do this calculation on a more simpler way, where delta 18 sulfate and delta 18 water is always linearly linked, and their slope is dependent on the pyrite contribution from the sulfate contribution to the sulfide. So if you have all the sulfide is coming, you are supposed to have a higher slope. If so, this FPY regulates the delta 18 sulfate and delta 18. The slope of this line, and FPY is linearly linked. So if you know this slope, means if you know the delta 18 of sulfate, which we have measured, delta 18 of water, the amount weighted delta 18 of rainwater is known to us. So if we measure the delta 18 of sulfate, we don't need to do the inversion, we don't need to go for a Monte Carlo simulation. Straight away we can compute the FPY, because they are linearly linked, and we did both the calculation, because the inversion allowed us to quantify all possible sources, and this forward model have helped us in quantifying FPY that is coming from sulfides, this amount of sulfides coming from pyrite. So that's what we computed, and these are some of the trends that you find. So in the Indus headwater, you can see this pink color. The highest part is actually the pyrites. If you see the sulfate, about 70 to 80% of that actually is coming from pyrite oxidation. We use that value to estimate the CO2 release rate, and also we have used these cations coming from silicates and carbonates to compute the carbonate weathering fractions, sulfuric weathering fractions, and plotted them to see whether this is a net CO2 consumption or CO2 release is happening, which is dependent on the alkalinity to DIC ratio. So based on that, we see that our most of the data fall in the second zone, where this serve like a long-term CO2 release and a short-term CO2 consumption. So basically, in this river basin, if you see this particular plot, the first blue color is a silicate weathering rate, then the sulfide oxidation rate, which is a positive, so because it is a supply CO2, whereas silicate weathering will consume CO2. So the net effect of Indus weathering in the upper reaches has a positive effect. That means whenever there is an intensity of the weathering of Indus upper basins is happening, they contribute CO2 to the atmosphere, and hence they cannot contribute to the cooling effect that we have been discussing on Cenozoic cooling. And more importantly, if you go down and plot to somewhere around Thata, which is the outflow of Indus to the Arabian Sea, at that location the silicate weathering rate dominates like many other rivers that has been discussed, and they serve as a net CO2 sink. But if you are looking at the Himalaya orogeny itself, then for northwestern Himalaya, surely they serve as a net source of CO2 and not net sink of CO2, as has been suggested to explain the Cenozoic cooling. So we don't find that in the Indus basin. So this is same story in a colorful pattern where we have shown all the basins. So if you compare the CO2, the red color are the release rates, they are much higher in the upper reaches. But if you come down and see in the near the outflow, the red color is less, which means the release is less, the CO2 consumption is more, so they act as a sink of CO2. So that's what we have found in. So we are sort of making more detailed calculations. These are very new results that I wanted to share with you, but more or less we are sure enough that in the Indus headwater, pyrite oxidation dominates and they contribute huge amount of CO2 to the atmosphere. With that, I will conclude. Mountain erosion process dominates the sulfide oxidation rates of river basins. The silicate erosion rates in the Indus headwaters are lower than that reported as global average for rivers. They are not very high as probably talked for many other river basins. The CO2 release rates via sulfidic oxidation, where carbonate dissolution is happening, is comparable to the CO2 uptake rate for the Indus headwater basin, and hence it is actually not comparable. It is much higher than the CO2 uptake rate, and hence has no effect on atmospheric CO2 budget. This outcome has a major implication because this clearly negates the earlier hypothesis, particularly from the northwest Himalaya. The northwestern Himalaya erosion has a minimal role to play, or even doesn't have a role to play in Cenozoic cooling. Before I conclude, I must thank all the contributors who helped me during this process. Of course, Rakesh, who did all the sampling, analysis, interpretation, everything goes to Rakesh Raut, who is a PhD student who completed his PhD very recently. Shreyas Mangave, Achyut Venugopal, Satya and Santosh from Wadia Institute of Himalayan Geology, Avhanan Singh Moria from Roorkee, and Zubir and Haider from University of Kashmir and Ladakh. They helped us in Leh.